I'm very glad here to introduce our work, Fast State Restoration in LLM Serving with HCache. First, I will talk about some basics about LLM serving applications and the motivation of our work. The naive usage of large language model is stateless, in which a query comes in, the large language model processes it, and once the response is generated, the HCache, the crucial state of large language model, is discarded. However, increasingly complex application of large language model today lead to a new trend, stateful LLMs. In modern use cases, a user usually provides a short input. The application will fetch a long context to help large language models generate high-quality data. The context is long and may come from many sources like database, website, or chat history. Both user input and the non-context is combined together to fed into the large language model and processed by it. The crucial part is that the reusable HCache of the non-context. If a new request come in and they share the common prefix with previous ones, its HCache can be reusable, leading to a faster response. But serving stateful large language model applications is challenging. First, let's look at the size of HCache. It's big. For example, with Llama 2 family models, the HCache size is 512 kilobytes per token for the 7 billion model and up to 800 kilobytes per token for the 13 billion model. To make the situation even worse, context lengths are usually long. For chatbots, we can see that over 50% of the sessions exceed 2,500 tokens. And in the RAG applications, it's even more long, with average context length reaching over 16,000 tokens. But the GPU memory is limited. Even with the high-end GPU like A100, it still can be constrained in how many tokens it can host. In fact, a single A100 can typically support only 7 to 30 conversation sessions or just 1 to 3 non-context tasks. Due to the limitation of GPU memory, HCache of many non-contexts have to be evicted when the GPU memory is full, and we have to restore it when we need it again. So the state restoration in LLM serving is an important problem. Let's briefly review existing solutions for this, starting with the first solution, KV offload. In this method, HCache is stored in the host storage. When it is needed again, it is transferred back to the GPU from the PCIe link. It's crucial to note that this solution, KV offload, solely depends on the PCIe transmission for the restoration, but it can be the bottleneck. The second solution for HCache restoration is recomputation. Here, the HCache is recomputed from the input text only. The text is stored in the host storage and is redoing the LLM inference, and we can get the HCache. It should also be noted that this solution depends on the GPU computation only. Let's take a look at the state restoration overhead. This slide shows the time to first token of these methods, in which we compare them with the ideal case, no restoration need. As we can see, existing state restoration methods introduce significant overheads during the restoration phase and can slow down the TFT by 6.5 to 26 times. So what's causing this? Our observation is that they utilize only one of the system resource. They use only one of computation and transmission. So they are underutilizing the system resource. To solve this problem, our work tries to explore how to simultaneously use both computation and transmission resource in the LLM restoration. I will introduce our key findings for this problem, the HCache. Let's start by revisiting the LLM structure. As you can see in the figure, each LLM layer has an input. We name it the hidden state. And in the right side of the slide, in each layer, the hidden state is projected into two KV tensors. The KV tensor is stored as the KV cache. Our idea is to store the input of every layer, the hidden state, for the restoration, and we name it the HCache, similar to KV cache. As shown, the stored hidden state, or HCache, can be used to restore KV cache by partially redoing the KV projection in each layer. Let me conclude how to use HCache. Assuming we already store the hidden state in the host storage, the restoration can be done in 3 steps. Step 1, we transmit the hidden state to the GPU. Step 2, we redoing the KV projection operations of each layer from the LLM weights. Step 3, we applying the positional embedding to the KV tensor, and then we can get the KV cache. Also, the restoration process can be finished in a simple pipeline. As shown in the right, step 1 of layer N can be done concurrently with step 2 and step 3 of layer N+1. So with this pipeline optimization, using HCache can utilize computation and transmission simultaneously. You can notice that the computation is the green box and the transmission is the blue box, and they can be done concurrently. Let me give a brief review of our method and comparing it with existing system. At the top left region, there are recomputation methods like VRM and deep speed. On the other hand, in the bottom right, we have KV cache offload methods, such as attention store and API serving. Our system, HCache, is the purple point. It is designed to strike a balance between the usage of computation and transmission, and we can use them concurrently. Moreover, HCache can reduce the I/O cost by 2 times and reduce the computation by at least 6 times less. You can see the details and analysis in our paper. So to summarize our findings, HCache allows us to efficiently utilize both computation and transmission, and at a low overhead. Next, I will introduce the challenges and the system designs when we build a system based on the idea of HCache. The first challenge is pipeline bubbles. As shown in the figure, when we run the simple pipeline introduced before, we often encounter idle periods, that's red boxes. On the left, on platform with high transmission bandwidth, in this case, the transmission is fast, so it causing gaps between data transfers. The situation is same on the right with fast computation. This bubble occurs due to imbalanced hardware capabilities between the computation of the transmission. Either of them can be fast or slow, so we have to find a way to adapt to it. The second challenge is the storage format. During the generation process, you can see in the left, hidden states are typically generated following a layer before token order. We essentially calculate all the layers for one token, and we proceed into the next token. That is the well-known auto-aggressive generation. It is the layer before token generation. However, for the restoration, the access pattern is token before layer. We visit all tokens in one layer first and move on to the second layer and the third layer. So the two access patterns are inherently contradictory. If you design one storage format for one access order, it is inefficient for the other. To address the two challenges, let me introduce our two important system designs. First, we propose a bubble-free restoration scheduler, which schedules how the KV cache is restored based on the different hardware capabilities. Next, to solve the mismatched storage format, we designed a chunk-based storage manager, which takes faster state restoration as its core design principle, but also want to influence the speed of generation. Let me move on to the first design point, the bubble-free scheduler. Its key idea is to combine existing different restoration methods together. You can see that in this slides, we can get the red line by combining the three methods together. It can adapt the computation and the transmission volume based on different hardware configurations. So the transmission time and the computation time can be almost the same. Maybe here is some design details for it. To combine different restoration methods, we first have to split the model state. You can see in the bottom left, for instance, we might allocate 4 layers for HCache and the last 2 layers with KV-cache. Next, we have to modify the pipeline in the restoration process. As shown in the bottom right figures, we can first restore the first 4 layers with HCache. Since the transmission speed is fast, and when the I/O is complete, the projection computation continues. At the meantime, we can fetch the KV-cache of the last 2 layers. It's an example restoration pipeline corresponding to the left figure. To determine the optimal split point, we achieve this by minimizing the delta, or the difference between the computation and transmission time in the system. You can find more details about this point in our paper. Next is the chunk-based storage manager. Our design principle is the fast restoration speed. So when we have to save the hidden state of one sentence, we will group tokens in the same layer into small chunks and distribute them round-robinly across different disks. In this way, as shown by the animation, it can enable concurrent read to aggregate the I/O bandwidth in the restoration. So this storage format is designed for fast restoration speed. Next, let's consider how to save into this storage format. A naive approach, for example, directly saving the hidden state into host storage is inefficient. Remember that hidden state, we say it generated in a layer before token order, which means hidden states are generated concurrently belongs to different chunks. This issue that if we directly save them, it will result in inefficient random writes to the host storage device. To overcome this, we introduce a 2-stage saving strategy involving a host DRAM buffer on the CPU, and the saving completes in 2 steps. First, we create a snapshot of the GPU's hidden state and copy it to a temp buffer in the host DRAM. Then we group the temp buffer into chunks, mirroring the chunk-based storage format discussed in the previous slide. Once organized as a full chunk, it can be flashed back to the host storage. It is a sequential large write, so it won't be the performance bottleneck. Okay, I've finished introduction of the major system design and move on to the evaluation. The basics of our evaluation is as follows. Setup of our evaluation is as follows. We compare our systems to 3 main alternatives: KV offload, recomputation, and the ideal baseline. Our testbed consists of 4 NVIDIA A100 GPUs and 4 high-performance SSDs. We also conduct evaluations on various cloud servers. Finally, we evaluate our system using representative LLM tasks like multi-round conversation and RAG applications. This slide shows the overall performance results. We're looking at 2 key metrics, TTFT and TBT, and 2 models on the various load rate. Our system, HCache, is shown in the blue. Its TTFT is consistently lower than both recomputation and KV offload, and the TBT is only 4% higher than the ideal case, which demonstrates that our restoration method has little overhead in it. Also, we done the sensitivity analysis on the various hardware platforms. We tested with different GPU models like A100, A30, L20 to see how different computation power it may influence the performance. We also test with various number of SSDs from 1 to 4 to examine the impact of I/O bandwidth. As you can see, across all the tests, HCache consistently outperforms our baselines by 1.33 to 9.05 times. This shows that our method can adapt to different hardware capabilities and utilize them efficiently. Finally, let me make a short conclusion. Our key finding is that we can catch in the input of the models of each layer in the model and restore the KV cache by doing the KV projection. And this method can utilize both computation and transmission resources simultaneously in the restoration phase with low overhead. Also, we introduced two key system design techniques: a bubble-free restoration scheduler, which combines different restoration techniques to adapt to various hardware characteristics. And we also introduced a chunk-based storage manager, in which group tokens into chunks and use a two-stage saving mechanism to avoid influence to the hidden state generation. That's all for my presentation. Thank you.